So once again, I want to welcome you to today's Research Pays Off, and I will hand it over to our presenter, Larry Sutter. And Larry, let's make sure you are unmuted.
I should be.
There we are. Yes.
Okay, thank you everyone. And I'm here to present today on a project that's just getting started at mnroad. Just kind of give you the overview of it. Really, I'm just gonna, as the outline says here, I'm gonna really kind of dive into where we're doing it, what we're doing, why we're doing it, and then a little bit more detail on what it is that we are doing and the timetable. So with that very brief introduction, let's go ahead and just jump right in. What we are doing is at mnroad. I presume many of you are familiar with mnroad, but in case you're not, as the picture depicts on the right here, in the lower right corner, what they do is they take a lane of, or they take westbound I-94, and they can route it. I don't know if you can see my cursor or not, but they route it onto what they would call here the mnroad main line. So all the traffic on westbound I-94 can be routed over onto the main line and then routed back on, and that can be gated on and off as needed. And that mainline section then is fully instrumented, and then it's set up so that we can come in and put in test mixtures of whatever you want to test, and put it down and test it under real world traffic. And again, this is Minnesota, so you're seeing cold climates, you're seeing all four seasons basically. It's a real world test of any technology you want to try to implement. The research at mnroad is administered and led by the National Road Research Alliance, NRRA, which is an affiliation of 11 different state DOTs, 50 industry representatives, associations, and academia researchers, all coming together to help conduct the research that is being performed here. The cells that are on mnroad are constantly changing, and what we're going to talk about today is some changes that are going to be happening over this next summer. So the specific project has been broken down into 3 different components. The first is going to be looking at the use of carbon dioxide for sustainable and resilient concrete pavements. The second is the use of alternative supplementary cementitious materials in concrete pavements. And then the third study will be looking at alternative cementitious materials. And I have here a hyphen geopolymer concrete. This basically these second 2 bullets, or the second bullet, is referring to things that we can use in concrete other than fly ash as a supplementary cementitious material. The third bullet is really referring to total cementitious systems that can be used to replace Portland cement. And then I'll talk more about the first bullet specifically when we get to more of the details. So then the big question is why? Why are we doing this? Well, there is a drive in the concrete industry to be carbon neutral by 2050. And this is in response to what we have all been experiencing increasingly for a number of years. As the old Buffalo Springfield song said, there's something happening here, but it just ain't exactly clear. There's definitely something happening here, and it's becoming more and more clear that there are issues that we need to deal with from a global impact, global weather changing, global warming, whatever we want to call it. Tornadoes are bigger and more frequent than ever. I often tell people that when I remember, I think it was 1974, there was a Category 5 hurricane in Ohio, in Xenia, Ohio, and I think it killed 30-some people and basically did to the town what we're seeing here in this one. And that was monumental. There really, in my lifetime, had never been a hurricane like that I recall. and it was just very unique. Now we're seeing those every year, and as we saw this last year, we had 4 or 5 of them occur at the same time in a very small part of the United States. It caused quite a bit of destruction. If you're living out west, you're living with wildfires. You're driving down the freeway going to work in the morning or coming home at night, and you're driving next to a wildfire. It's just become commonplace to have the state on fire and burning, and it's not normal, or it should not be considered normal. And if you live in other areas of the United States, you're seeing hurricanes like we've never seen in terms of the intensity. As I said here in the slide, we're seeing 100-year storms every other year. So there's something happening here, but it is becoming very clear that there's something going on in terms of the environment. And right or wrong, however you want to look at it, we have made the decision to start moving towards decisions that are going to limit the increase in temperature of the Earth over the next 50 to 100 years. The common I guess the commonly accepted pathway that we want to get on is what's referred to here as the 2 degrees C pathway, the green line on this plot. And what that means is on the y-axis we have CO2 equivalent per year being emitted, greenhouse gas emissions. And if we can limit those, as shown on the y-axis, then we can start seeing a reduction in temperature. And by 2100, the average temperature of the Earth will increase by only 2 degrees C or 3.6 Fahrenheit. So that's the goal, is try to get on that green line. If you were to take every promise that's been made, we have the Paris Accords, the Kyoto treaties, all these different things that we've heard about in the news. If you take everything, every promise that's been made, and we lump it all together, and we say that's what we're going to do, that's the red line. So that's the path that the best scenario path that we're on. If we do nothing, if we just keep business as usual, keep moving forward, we're going to be in the blue line. And so if we want to get on the green line, we have to start making some changes. If you look at the x-axis time-wise, somewhere around 2024, 2023 is where that curve starts to bend south. So if we want to start making changes, we need to start making changes now. And the cement and concrete industry have made the commitment that they're going to be carbon neutral by 2050. Why? Cement accounts for about 5 to 8% of the man-made CO2 produced in the world. It's been often said that if cement industry was a country, it would be the number 3 emitter of CO2 behind China and the US. So decarbonization of the cement and concrete industry is a high priority. There's a number of roadmaps that have been put out. I'm not going to beat you over the head with all the different roadmaps. Right now, you probably could come up with at least 20 different roadmaps that have been laid out by different individuals, different groups, different things. The bottom line of all these roadmaps really comes down to the same basic message. How are we going to do it in terms of cement and concrete? How are we going to do it? Well, here's the 5 steps that we pretty much all agree on in some form. We're going to do it by mixture optimization, which means using less cement per cubic yard of concrete. We're going to do it by increased use of supplementary cementitious materials, which means that per yard of concrete, per pound of cementitious material, we're going to have more of it be an SCM and less of it being Portland cement. And we'll talk more about that in a moment. Dematerialization basically is using less concrete. So coming up with designs of structures and components and structures that simply use less concrete. So we have less concrete, preferably with less cement, but at least less concrete. Carbon sequestration is going to be probably the final holy grail, if you will. we need to figure out how at the point of production, at the cement plant, how to sequester CO2 that's being generated and not release that CO2 into the atmosphere. And last is going to be material substitution. So that really is going to be just taking Portland cement completely out of the picture and replacing it with something else, or an alternative cement, as it's often referred to. This is a little problematic because as a society, we have just become completely dependent upon Portland cement concrete. We have things in our society that it's a cornerstone of society. It could not exist. Dams, water treatment, go on and on and on. All the things that we use concrete for that are just absolutely essential. So I don't know if Portland cement concrete will ever disappear, but there are certain applications where other materials could be substituted, and roads and to some extent bridges are possibly one of those applications, and that's what we're really going to be studying at the mnroad facility. We're not going to be looking at the dematerialization issue in particular, the idea of making things, that's really a design issue. How do you design things differently? But with the study we're going to do at mnroad, we'll touch on all 4 of these other bullets. So the project specifics that we're looking at is we're going to, first of all, construct 6 test cells at mnroad that are going to be maybe, well, in some sense, one will be a control mixture, but the other ones will be dealing with kind of the low-hanging fruit, if you will. So the control mixture, we'll talk more a little bit about that in a moment. The optimized mixture is a mixture where we're going to simply take cement out of the mixture. So that would be, the idea of just reducing the amount of cementitious being used. PLC is Portland limestone cement. As we move into this construction season, most Midwestern sources of cement are no longer going to be standard type 1 Portland cement, but they're going to be a PLC, which is a SCM C595 blended cement. And it has up to 15% limestone in it. This is going to be the norm moving forward. And we are going to then, at mnroad, start looking ahead to the next hurdle or the next milestone, which is going to be how do we move that out further. If you look at Europe, 25% replacement of limestone and cements is not uncommon. And so we want to get some pavement on the ground that is looking at these higher replacement levels of limestone to see how they perform. Carbon Cure is a technology that's out there right now where you can inject CO2 into concrete. And we'll be evaluating that technology as well for use in pavements. It's already being used in a number of applications, ready mix applications. Then the remaining test cells are going to be either an alternative SCM, which again, looking at materials to replace fly ash in our concrete, because fly ash is also something that's going away as coal-fired power plants are being shut down. Fly ash supplies are becoming more challenged. And then last, to look at alternative cements, basically replacement materials for Portland cement. So in more details yet, the control mixture is going to be a standard Minnesota DLT paving mixture. All of the control mixtures and all the mixtures that use Portland cement are going to be using the C595 Type 1L blended cement, which is going to be 10% limestone. So no Type 1, ordinary Type 1 Portland cement will be used in any of this construction. All the mixtures we're going to prepare are going to use the same coarse and fine aggregates, probably in different proportions depending upon the cement that's used, but it'll certainly be the same material. All of the materials are going to be required to be processed through a conventional ready mix operation and placed using a slip form paver. So that applies to all mixtures we're looking at in this study. The optimized mixture is taking advantage of some things that have been developed and have been gathered in a new document, AASHTO PP84, Performance Engineered Concrete Pavement Mixtures. And that is to look at optimizing the mixtures, which involves essentially removing the cement from the mixture and optimizing the aggregate gradation in order to achieve the same level of performance in terms of strength and permeability and other measures relative to the higher cement concrete mixtures. The Portland limestone cement, the PLC mixture, for that mix, we're tentatively looking at probably something on the order of 25%. Currently, the standard limits the Portland limestone substitution to 15%, but we want to push it out farther. So we're going to be looking at 25% as the replacement level. Almost certainly, we're going to blend this 25% PLC with a fly ash to produce a ternary blend. And that is because research has been conducted by Jason Weiss at Oregon State. A number of other people have shown that there's a synergy between the fly ash and the limestone replacement that really helps to allow for this higher replacement level and still achieve the same level of performance. But the specific blend is yet to be determined, and we are working through some of these details yet. So I mentioned carbon cure. Many of you might be familiar with carbon cure. It's a technology where you inject CO2 into the ready mix mixture right in the truck. And then what that allows you to do is to sequester some CO2 into the concrete. But through the effects of the carbon cure CO2 injection, you're also then capable of taking some of the cement out of the mixture because of improved properties that you get by using the carbon cure. And so this has been used, I'm not sure it's been used in paving, but it's been a limited application. And the intent here is to evaluate this technology for paving. So what we're going to do is take and use the control mixture that I mentioned, the mndot paving mixture, injects the carbon cure into that, and that'll be one test. The other will be to take the carbon cure designed and optimized mixture. So let the experts at carbon cure design and optimize the mixture that they feel is going to perform the best using their technology and place that. And then the third will be to take that mixture that they designed and make the same mixture just without the CO2 injection to be able to monitor the impact of the CO2 injection on the overall performance of the concrete. So we have 3 different test cells that are going to be dedicated to the carbon cure technology. So the remaining mixtures then are going to be looking at alternative SCMs and alternative cements. So again, a supplementary cementitious material, or an SCM, is intended to be a material that we use to replace cement in a mixture. And typically we use fly ash or slag for that purposes. As I mentioned, fly ash is becoming challenged in terms of supplies, at least in some geographic areas. Some areas it's not an issue, some areas it is. And so we're trying to find alternatives to fly ash. And some of the things that we're going to be evaluating are natural pozzolans. Natural pozzolans are materials that occur naturally, as the name implies, but they have the same chemical or physical benefits that we see from fly ash. These are primarily available in the western states, and so we have two cells, dedicated to looking at natural pozzolans. Ground glass is a relatively new material that's been developed, or has been recently an ASTM specification developed for it. It's basically consumer glass that has been ground extremely fine to cement fineness, and then it can be used as a pozzolan. It's extremely pozzolanic, very, very high performing material. And we will be evaluating that in the one cell dedicated to ground glass. Another thing that's happening in the SCM world is harvested fly ash. So as I mentioned, fly ash is becoming more difficult. That's really in reference to freshly produced ash. The number of coal-fired power plants out there is diminishing. However, there are probably easily a couple billion tons of fly ash that have been disposed of in landfills and impoundments, and that material now is being harvested. This again is something that's been going on in Europe for 20 years, and now we're starting to turn our attention to it here in the United States, and that's to take the harvested ash and evaluate it for use in concrete. It is being used currently in concrete. So the material varies in terms of how much processing is required in order to use it. And there are some questions about, its long-term durability and so on. So it felt like it was important to include a harvested ash source in the study. Manufactured SCMs, there's a number of companies out there that are producing manufactured materials, synthetic materials, manufactured materials that are SCMs. They perform like a fly ash or a slag in the cement. They provide the same benefits. And there's 2 or 3 different technologies that will be evaluated in these in this general class of materials. Again, they are intended to be a direct replacement for fly ash, and so we will use them in this study as a direct replacement for fly ash, and obviously gauge their performance as we move through this. The remaining mixtures will be alternative SCMs. And this is going to be probably the newest territory we're going to be moving into. A lot of this other stuff that I've already talked about is things that has been done to some extent, but the use of alternative cements is something that's not really been done, particularly in the paving world. I'm sorry, this is the same slide. Alternative cements, yeah. So these are cements that can basically serve as a complete replacement for Portland cement in a concrete mixture. And we're looking at basically 3 different types of materials. First is LC3, and I'll talk more about that in a moment, but it stands for, the L is limestone, the C is clinker, which is used to make Portland cement, and other C is calcine clay, other 2 C's. And we'll come back to that in a moment. 1157 cements are hydraulic cements that perform like Portland cement, but they are not Portland cement. They are quite often blends that involve clinker and other materials, but they are not a Portland cement. They've been around for a long time. The 1157 spec has been out there for probably 30 years, if not more. But now, all of a sudden, again, when people start looking at this idea of sustainability and reduced CO2 footprint, these materials have become very interesting because of the clinker reduction. Again, as I mentioned, 5 to 8% of the CO2 in the world comes from the production of cement. So the underlying theme in all of these things here is how do we use less cement? 95% of the CO2 that's associated with concrete comes from the cement. So we're looking at different cements, different cementitious systems, because that is the most significant lever we can pull to make a difference. The other technology we're going to be looking at is alkali activated cements. Often these are referred to as geopolymers. I like the term alkali activated better. I think it's a little bit more descriptive. And we'll dive into each of these in a little bit more detail, starting with the LC3. LC3 is a relatively new technology. It's been developed. It's been used actually for paving in India. It's been used in a number of different construction applications around the world. It has not really made its way to North America yet, but it very slowly is. And you can get up to a 50% reduction in clinker by using an LC3 cement. So basically, we're going to take our CO2 emissions and divide it in half, roughly speaking. It's closer to 40%. But we're getting rid of the major component by reducing that clinker, and then we're going to replace it with limestone, calcined clay, and then gypsum. So gypsum, of course, is part of Portland cement. It's always been there. Limestone, again, there's a synergy that's been shown between ground limestone and SCMs like fly ash. And in this mixture, the SCM that's being used is calcined clay. So that is probably the most, the biggest difference between what we would consider a conventional concrete mix and then this technology is the calcined clay. Calcined clays have been used in concrete. Many of you may be familiar with metakaolin. That's the product that's been out there. But calcined clay is basically addressing the issue of an SCM. So if fly ash is really becoming more difficult to come across due to the reduction in coal combustion, which it is, then what are we going to replace it with? And we start looking around the earth and trying to figure out what kind of materials do we have in large enough quantities that we can actually live with it for a extended period of time, 50 to 100 years. We're looking at calcined clay. That's really the only material that's out there that's in any level of reserves that can even begin to rival what we have with fly ash. And it can be produced in the same production facilities as Portland cement. So basically, this material, we can basically have a turnkey operation, really, where you just convert from Portland cement production to LC3 production, which is why it's really attractive to the industry, is because the cement industry is extremely capital intensive. And if we don't have to reinvent the wheel, that makes life a lot easier for everyone. And, if the cement industry has to go in and reinvest in all that capital in order to make a new technology, the consumers are going to see that in the price of the product. So everyone wins if we can build off the existing technology we have. So this is really kind of the underlying idea behind LC3. And so we think it's really important to have an LC3 test site in this mnroad facility, and so we will. And we're shooting for the 50% clinker replacement. Other blends have been made where you have a 30% or a 40% replacement, but we're shooting for a 50% replacement in the LC3. Alkali activated materials, again, have been around for a while. There are some who have opined that the pyramids of Egypt were not actually cut stone, but were actually cast in place, or at least partially cast in place using alkali activated cements. And I don't want to go down that discussion too deeply, other than to say that it's a fascinating discussion. But alkali activated cements are basically different than Portland cements in the chemical reaction that occurs. In a Portland cement, it's what we refer to as a hydraulic cement, where we take water and the cement and mix it together, and we get a chemical reaction where the water becomes part of the actual solid that is formed. We form hydrated minerals. And this plot tries to summarize kind of the difference between all these different technologies that are out there. And as you see, if you move up on the z-axis, go up along the screen, you see increasing calcium content. And generally speaking, as the calcium content in your cement increases, you're going to see it be more of a hydraulic cement. And then as you start moving out along on the basal plane here, M plus is indicating sodium and potassium, or alkali minerals, and then moving along the other axis, increasing aluminum content. And so if you move out away from the origin, if you move towards more aluminum, you can get what is actually a geopolymer, which is a specific type of reaction that occurs. As you have less aluminum, but limit the calcium and increase the alkali, you're going to get alkali activated materials. So basically, an alkali activated cement tends to be a lower in calcium cement that chemically reacts with the alkalis to form a hardened material. A geopolymer is a low calcium, high aluminum material that interacts with the alkalis to form a material. And then the Portland-based cement, the calcium sulfur aluminate cements, and the calcium aluminate cements are cements that are higher in calcium and react with water to form reactions. So they're not reacting with the alkalis, they're reacting with the water. So again, it's probably more chemistry than most people would want to get into, but this is kind of the space that we're living in. And right now, this alkali activated material and geopolymers is something that's getting a lot of attention. And you know, it remains. I guess it remains to be seen. I guess the short way to answer this is it remains to be seen how these materials are going to perform. How can we work with them? There certainly have been pavements and paving operations that have been done with geopolymers. Just there hasn't been any in the United States, and to my knowledge, there hasn't been any in cold climates. And so it's going to be interesting to see how these materials perform, both from a paving perspective, but also then in a cold climate durability perspective. So when is all this going to happen? Well, construction is planned for the summer, so we're moving very quickly. We have a lot of things that have to come together over the next 4 to 6 weeks, finalizing the material selection. We need to get the contractors in place to provide the materials, provide the construction, and kind of get everybody on the same page. And we are very quickly moving ahead with that. The material providers, the people that are providing the unique materials, they're going to be charged with developing the mixture designs and evaluating the mixture performance and providing data on their environmental impact that we can use to evaluate the material. And of course, they'll be involved, they'll be responsible for the logistics of getting their material to the mnroad construction site. And that's going to happen over the next 4 to 6 months. They need to gather that mixed design information and work on it. So that's just beginning. So the final mixture designs have yet to be finalized. We would like to have for every new material that's going to be used an environmental product declaration or an EPD. The problem is that we really can't do that specifically. Number one, they don't exist. And number two, one of the reasons they don't exist is because an EPD has to be developed under the guidance of a specific product category rule. And right now, there isn't a product category rule out there for these alternative materials. Now, with that being said, we can still evaluate the environmental impact. And that is going to be a big part of what happens in this project. What's going to happen is after construction occurs, there's going to be 3 different research projects that have already been contracted or they're under the process of being contracted. And it's going to be the responsibility of those researchers to look at these various materials. And again, the 3 different groups are the carbon cure materials, one group, alternative SCMs is the second group, and alternative cements is the third group. The researchers are going to look at durability, they're going to look at performance, all these other things, but one of the big things they have to do is to get the data that's available on these various materials, and in essence, develop an EPD, although it's not going to be an official EPD because there is no product category rule. It's going to be an EPD-like assessment of these materials, because in the end, yes, we very much want to know how these materials are going to perform, but we also want to know how they're going to perform from an environmental perspective. And I guess the simplest way to say that is if there is an environmental benefit, if there isn't a CO2 savings, then a particular technology probably is going to be less interesting than a technology where there is a CO2 savings or an environmental benefit. So we have to, in addition to evaluating the performance as a concrete material and as a paving material, we also need to evaluate the environmental impact of these materials, because in the end, that is the driving force for why this entire research project is being done. The DOTs involved in this project understand that the train has left the station. The industry, the cement concrete industry, is moving to be carbon neutral. Alternative SCMs are going to be part of that. Alternative cements are going to be part of that. And we're going to still keep building roads. We have to learn to start building roads with these new materials. And this is going to be a major step towards being able to do that. This material, this research project, in my opinion, is going to be a very important stepping stone towards getting these new materials into road construction. And we're going to demonstrate performance in one of the most harshest environments that we can demonstrate it. And so, in other words, if it works there, I'm not going to say it's going to work anywhere, but I feel a lot more confident about working anywhere. We have very strong support for this work from the Federal Highway Administration, from the DOTs, and from industry. Everyone's at the table. Everyone sees where this train is going, and we are trying to get on it and be part of the solution as quickly as possible. And so I really applaud mnroad and NRRA for the leadership that they are showing by taking on this project. As I said, after placement, the performance is going to be monitored for at least 3 years under separate contracts. And as I already stated, it's not just going to be the performance as a paving material, but it's also going to be performance from a CO2 from an environmental perspective. All the information that comes out of this obviously is going to be public information. It's going to be presented widely. You're going to be seeing a lot more about this. And hopefully it's going to guide all the DOTs, not just the ones that are involved in NRRA, but all the DOTs in their transition to a more sustainable paving material and a more sustainable paving future. So with that, I would be happy to take any questions that you might have about this project or about these technologies in general. I thank you for your time.
Thank you so much, Larry. I don't see any questions or comments in the chat so far, but if anyone has anything they'd like to say, please go ahead and you're welcome to unmute yourself to ask your question. Oh, I do see a hand raised from Sutter.
Hi, yes.
Yeah.
Thank you so much for the presentation, Larry. It was very interesting. I have 2 questions, basically, like 2 directions. One of them is, you mentioned carbon sequestration, and we know that in general, calcium and magnesium, I think, they do some natural carbonation when we have them in concrete infrastructure. Now, one of the mitigation methodology was to reduce them through geopolymer by adding more aluminum, I guess. Has there been any assessment on whether, well, let's say, what would be the overall sum of carbon reduction we're doing in terms of reducing this natural sequestration of carbon that happens with calcium and magnesium versus aluminum? So that's the first question. The second one would be, are there, so I know these are, based on these studies, the clinker produces this amount of CO2, and this is the biggest part. And then if we use less, we're basically contributing to the overall net zero goal. But what are the methodologies, like monitoring methodologies out there to actually assess that? Do you guys have any hands-on experience with that, with like measurement of carbon emission or life cycle analysis? I would be very interested to know what would be, or what are the strategies you guys can employ for this. Thank you.
So the first question, it's actually, I thank you for the first question, actually, because it's actually a dimension I had not thought about, but it's definitely a dimension that needs to be considered. So I guess maybe just as part of the answer, I'll restate it. But so concrete is very rich in calcium, and concrete carbonates, Portland cement concrete. So as we place a concrete road or a bridge, that concrete which is exposed to atmosphere absorbs CO2 and carbonates, and it absorbs that CO2 permanently. Now, part of the roadmap that has been proposed by some people is to rely more or less on this as a component of the roadmap. There's a number of issues with it. First of all, is that it's only concrete that's exposed to the air that's going to carbonate. So if you take a bridge abutment or a major mass concrete structure, it's going to carbonate maybe to 10 millimeters in depth, something in that order, over 15, 20 years. So the vast majority of that concrete is not going to carbonate. It's not going to uptake CO2. However, some of the concrete does, and it should not be forgotten, and it should be considered in any balance, any CO2 balance that we're trying to look at. And you're right that if we replace that Portland cement concrete with a geopolymer, it most likely will not carbonate because it is going to have less calcium in it. And so it is going to, whatever that contribution is, it is going to be less. So as we go through the process, or when I say when the research teams go through the process of evaluating the environmental impact, that's a factor that we need to consider. And again, I'm glad you brought that up because I've made a note of it now, and I'll make sure that the research teams are thinking about that. There's a really interesting sidebar to that too, and that is our conventional roads right now, Portland cement concrete roads, they carbonate, and so we have a lot of surface area out there that is exposed to CO2, and that is actually something that we could be doing on a regular basis, is that we could be out milling those roads and exposing new concrete to the atmosphere, uptaking new CO2, and at the same time getting the benefits of milling the roads, improving the road quality or ride quality, and those types of things that could occur. So it's actually kind of an interesting idea, is the concrete, using a normal Portland cement concrete as your pavement material, you actually kind of have a renewable CO2 sink there that you can make use of. And again, from the standpoint of thinking about the CO2 balance, I think that's something that we ought to be thinking about as well. So you've put definitely an interesting problem on the screen for the research teams to be thinking about. The assessment question is a different story. There's a couple different aspects to assessment. First of all, from an EPD perspective, that's fairly straightforward. The methodologies for assessing the CO2 footprint of the material is, I would say, is life cycle analysis, all that type of thing, is pretty well established. The only real question is, where do you draw the boundaries? So you have to, put boundaries around the system somewhere. And so that is always kind of the difficult question: where do you draw the boundaries? And that's something that we have to consider as part of this research project. We have different materials coming from different parts of the United States, travel, hauling, all these different things. We have to think about it. But the production of the material itself, you pretty much can identify all the factors of production and assess the CO2 footprint of that. You know, you look at Portland cement, you look at slag. There's already EPDs out there for those materials. I know fly ash is discussing and developing an EPD for fly ash. It's a little bit more challenging, but it can be done. So, you know, the LCA side of it is doable. The other side of it is, when it comes to assessment, is how much CO2 is actually being taken up in the material. So if you look at all the various technologies that are going to put CO2 into material, how much CO2 is going in? So, for example, we just talked about the natural uptake of CO2 by Portland cement concrete. How do you assess that? I mean, are we going to go out and core every structure and look at the depth of carbonation and try to, I mean, how do you, we're not going to do that, obviously, so how do you do it? And there's other technologies that are coming out now that that are far more subtle in terms of how they entrain the CO2 and how do you measure that? That's a real challenge. The National Institutes of Standards and Technologies, NIST, currently has a research project going on where they are looking at the second question: how do I measure the amount of CO2 the sequestration technique has actually sequestered? And that is a difficult question, and hopefully in the next 2 to 3 years, NIST is going to come out with some recommendations on how we do measure that, and hopefully that's going to in turn be translated into ASTM standards that we can use to directly measure that carbon uptake. So you've identified two areas that are definitely wide open, and two areas that this research, I think, is going to provide significant contribution to.
Thank you very much.
All right, and then we also have, yes, a question from Peter.
Pete Kemp, Wisconsin DOT. Wondering if you could just, well, a quick comment as you take a look at grinding and the additional CO2 uptake. You can also consider, obviously, fuel economy and the increase seen from RIDE.
Yep.
And so that'll, I think, be more of a major contributor in that calculation than would be the CO2 uptake.
Yeah, that's a great point.
But my question is, you know, carbon cure. I don't know if you just briefly touch on how this works and where this carbon is that is being sequestered. Where does this come from?
I mean, what is the source of the CO2 itself?
Yes. What do we see?
I believe they're using post-industrial sources of CO2. So if you are a ready-mix producer and you invest in the carbon cure technology, what you get is a tank that you periodically fill with CO2. They send the CO2 truck out there and they fill it up. You have a box that meters the CO2 into the mix. The CO2 is injected into the mix as the concrete is being mixed. Some of that CO2 remains in the mix. Some of the CO2 does not remain in the mix. The CO2 that remains in the mix, some of it goes to form calcite, calcium carbonate, and that calcium carbonate, very coarsely described, acts in a way similar to the way Portland limestone acts in the Portland limestone cement. The limestone and Portland limestone cement really provides this benefit from two different sources. The first is that it chemically reacts with the cement to form carboaluminate phases. I personally think that contribution is small compared to the second contribution, but that is a contribution that a lot of people like to point to. I think the more important contribution is that, and this is where carbon cure, I think, also is getting its benefit, is that the calcite that forms when you inject that CO2, or the calcite that is in there when you intergrind limestone, acts as a nucleation site for hydration products to form. And this is a real common, a very well-known component of material science, is that when you want to solidify something, you put in what we refer to as seeds, or you put in what we refer to as a scaffold, something for that first point of nucleation to occur at. And that speeds it up. And that's what happens, I think, with the CO2 injection, and also with the limestone, Portland ground limestone injection, is it provides that scaffolding effect. And so hydration products form react more rapidly. And the synergy that comes from fly ash is that as the Portland cement is reacting, it's producing more calcium hydroxide, which in turn is reacting with the fly ash. So the fly ash is reacting more quickly as well. And so the net result of putting these seeds in there is that all these reactions that normally took 7 or 28 days, or however you want to think about it, are being sped up. We're getting strength earlier, and we're getting more complete reaction. Whereas in a Portland cement concrete, you open it up and look at it, you're always going to find grains of cement that never reacted. With the addition of the ground limestone or the carbon cure, you're going to get a more extensive reaction of the Portland cement. So all these things contribute to a higher strength, and then allows you to take some of the cement out and get the same strength as you had with pure cement.
Thank you.
We still have a few more minutes left for our day today, but so if anyone has any other questions, feel free to chime in.
Hi, Sutter here again. I might follow up on that monitoring question. Larry provided some information about NIST. So basically, for existing infrastructure, the only way to kind of see how we're capturing naturally CO2 is through the depth of carbonation as of now. Like, that's the only methodology that's basically destructive, if you will.
Yes. It's a little bit more involved in that. So depth of carbonation is something that you could, if you took a core, there's very simple techniques you can use to measure that depth. But what you don't know really is the extent. We don't know. I mean, for example, on the surface of concrete, when it carbonates, not every single calcium atom in there is going to carbonate. In fact, probably a small fraction of them are. So you really need to look at the CO2 uptake itself. And there are analytical techniques that you can use to measure that. But concrete is a real finicky material. I mean, it's got inhomogeneity at pretty much any scale you want to look at it, from the atomic scale up to the macro scale. And so making measurements that are absolute are very difficult to do in concrete. So it's more than just a depth. It's a matter of really doing a chemical analysis to find out how much CO2 is there. And then from there also trying to understand, well, okay, how does that one measurement, or how do those average of 3 measurements or whatever it is, represent the entire block, the entire piece of concrete. And then there's this inherent errors that are associated with trying to measure CO2, and just analytically speaking, but there's also errors associated with what's the source of the CO2. You know, is the CO2 part of the natural minerals that were used in the actual making of the concrete? You know, for example, if you use limestone as your aggregate, you have CO2 there. Mm-hmm. And if you are going to do an analytical technique, that's going to report as CO2. So how much of the measured CO2 was already there? How much of it has been taken up because of sequestration? there's a lot of scratching of the head that goes on. So it's not a trivial analysis. Measuring the depth is trivial. That can be done very simply, but that's only kind of a thumbnail sketch of what is really happening.
Got it. Thank you.
You can, however, draw, I think, some conclusions from the depth. You know, in other words, if the depth on concrete A is twice as much as the depth on concrete B, I would, as an engineer, feel pretty confident saying that the first one took up twice as much carbon as the second one. I don't know what that number is.
Yeah.
I would say,
especially if you keep it under the same environmental condition, you could, effectively make that conclusion.
Yes, and it's not going to be exactly twice as much, but you know, as an engineering estimate, it's probably close enough.
All right, and Bernard has his hand up.
Yes, thank you very much, Larry. I just wanted you to clarify something concerning the way of tracking the sequestered carbon dioxide. Maybe it's an opportunity for you to shed light on that. Now, if we adopt a method whereby we know that the aggregate component of the mix, when it's still very plastic, is really not, it's going to stand in the way of tracking the CO2. And we know that the stoichiometric approach is going to be a little bit cumbersome. If we decide to filter, to do a wet sieving or a sieving of, let's say, an alcohol injected, a sample that with some ethanol injected in it, or some volatile compound or something that will preserve the mix for a while. And then we do the wet sieving and we take that sample, make, maybe a cylinder or a beam, and then do some petrographic analysis after X number of days. We do that on the control as well. Now, would we, to an extent, not be able to see a difference in a petrographic analysis between the result of the sequestered CO2 because of probably the structure of the calcium carbonate formed, of the calcite formed, will be different from the regular structure that you would ordinarily have in the concrete. Would that not be a, let me say, a feasible, more or less a feasible compromise between the stoichiometric approach and the no approach at all?
I think in general, the answer is yes, but I think practically, I think the answer is no, because I don't think that you're going to find, if what we're talking about is CO2 injection, CO2 sequestration from injection of CO2, I don't think you're going to find a detectable level of calcite there that you can actually go ahead and measure that petrographically. Now, if we're talking about calcite from limestone, like in the Portland limestone cement, well, that's 10% of the cement. So yeah, you're going to find that. But the CO2 that actually gets uptake from the injection is not that much. But the flip side of it is it doesn't take a lot. I mean, if you're forming these seeds that I described, you don't need a lot to get this process to move in the right direction, to speed up and to accelerate. And so, I guess that's kind of would be the answer. There are other technologies that are being developed that aren't out in the market yet for CO2 injection that fall somewhere between what we currently have with the carbon injection for carbon cure and the carbon that we would see from a Portland limestone cement. And those are the ones that we want that's what we need to develop this methodology for. And I guess until we start working with these and seeing these other materials, it's going to be hard to say. As I said at the start, I think that the process you outlined makes sense experimentally. I just am not with the current sources of CO2 for sequestration. I'm not sure we would see anything. Another thing is that some of the sequestration that's being done to the components. So, for example, there is one company I'm aware of that is carbonating fly ash. And then then they have CO2, and then they put that into the concrete mixture. Then that's going to chemically react. Fly ash is going to chemically react. And then where does that CO2 go when it reacts? No one has looked at that I know of. And is it going to go into, does it form a gas? And does it diffuse out of the concrete? Does it form calcite? I mean, I don't know. So what form it's going to be in, I guess, is really a kind of a wild card. And I think that this research project, like many research projects, is probably going to spawn as many questions as it's going to answer. I think this whole issue that you're getting to, how do we measure this, is a really, really key question that we need to think about in this research. There is, going back to my original answer, right now there is no good way to measure CO2 uptake in concrete, and there is no simple way, other than to look at depth of penetration and make some thumbnail guesses. And we need, for quality control purposes, for quality assurance purposes, and for just understanding what we're doing that makes a difference, we need methodologies for measuring CO2 uptake. So it's going to be a challenge. That's the best I can say at this point. There is no good way of doing it.
Thank you.
All right, well, we are just past the hour now, so I know some people had to drop off, but we will close it out here, and Larry's contact information is on the screen, so if you have any other follow-up questions, I think, he's welcome to take your emails. And we will say goodbye for today and see you next month. Thanks so much, Larry.
Yeah, thank you, everybody.